Hello, hello, everyone. Welcome to another online tutoring session. Just wanted to let everyone know, so this session is going to be an hour long, and I will be answering questions at the end. Today, I'm just going to be covering naming compounds, some balancing equations, and stoichiometry. And then I'm also going to mention that if you want to save your spot for next week, I do recommend doing so. You can see that on the screen. There's a green button that you guys can see that says save my spot for next week. So at any time, click that button just to make sure you join us again on Sunday. All right, so I'm going to go ahead and start. I'm going to start off with doing some naming compounds. All right. And so the main thing that whenever we're naming compounds, we always want to start off with just knowing what type of compound it is to begin with. That is the strategy that I actually like to do and use. So let's say if you automatically see that it's an ionic compound, just remembering ionic compounds always have one metal and one non-metal. So your metals are going to be positively charged and your nonmetals are going to be negatively charged. So that's an ionic compound. Now, a covalent compound is instead going to just consist of two nonmetals. I'm going to be going over all the different naming rules for ionic compounds as well as covalent compounds. All right, so let's start with the first one where it's just going to be ionic compounds without a transition metal. So once again, without a transition metal. What that's going to consist of, it's going to be the name of a metal and the non-metal ending in "ide." So that IDE is very important because it's actually going to tell you it's only one element. So in our case, let's say we have aluminum oxide, aluminum being Al, and then oxide just showing that it's oxygen. So that "ide" is going to refer to just one element. That's very important to note. So once again, "ide" is just going to refer to one element. For ionic compounds, you are always going to be balancing out your charges. So in our case, if we were having aluminum oxide, we're just going to have that aluminum with a 3+ charge, oxygen with a 2- charge. And then you want to balance out the charges. So what I want you to think of is think of it kind of like a lowest common denominator. That's what I always like to think of, where in our case, 3 and 2, our lowest common denominator would be 6. So we want to actually get our charge to equal 6. So in this case, aluminum will need 2 more and oxygen will need 3 more. Let me go back. So in this case, our final answer would then be Al2O3. And I'm going to keep going over these types. And I'll go into the next one. This next one's really important to know. This is an ionic compound with a transition metal. The difference is going to be that there is a Roman numeral in the middle. And that Roman numeral is actually going to tell you the charge of your transition metal. So in our case, if we were to have iron 3, that's actually going to be Fe with a 3+ charge. And then we'll also have a nonmetal ending in "ide." So once again, we'll have oxygen. As I mentioned before, that "ide" refers to just one element. And then once again, we have to balance out our charges. So this would have been 3+ and 2-. And it's going to still be that we want it to be a 6 charge so they can cancel out and be neutral. So in our case, I want you to think of this as, some of you guys have learned this as like lasso, where we'll put that 2 with the Fe and that 3 with our oxygen. And that's how we know it's iron oxide, just showing you how many more iron you need as well as oxygen. And there will be time to practice afterwards. Before I move on to the next one, I just want to make sure how we're doing. Is this all making sense? Go ahead and write down in the chat. Just let me know, is this making sense? Just to hear your feedback. Yes. Chris says yes. Jessica says yes. Okay, great. I'm going to keep going on. So what I'm showing right now is just all the different combinations of ionic compounds that you will possibly see. The next one is going to include those polyatomic atoms. Now, I do have different tricks for you guys to actually remember polyatomic atoms because I know there's so many. For polyatomic atoms, so I'll get into the trick soon, but specifically for polyatomic atoms, that just means that there's going to be two or more elements within the atom or the compound. So I went ahead and just included a list right here of all of the common polyatomic atoms that you're going to see on your exam. And what this consists of, it's going to consist of the name of your metal and your polyatomic atom. So in this case, we have calcium phosphate. The majority of your polyatomic atoms will end in ate or ite. And this is just a clue that it tells you that it's going to be a polyatomic atom. So I just know that if it ends in ate or ite, I know it's polyatomic. However, if it ended in ide, it's most likely going to be just one element. So I'm going to go into the trick right now. So let's say if we were to have sulfide, sulfate, and sulfite. So I'm just going to show you what the ending really tells you. So that ide portion tells you that this is just going to be one element, meaning it's just going to be sulfur. So S. That ide told me it's one element, so it's just sulfur. Sulfate, that ate, then tells me it's going to be polyatomic. Same goes for sulfite. That ite then also tells me it's going to be polyatomic. Now, there's a trick with this. I like to think of I ate more. What I mean by that is I ate more just stands for there are more oxygen with the 8. So sulfate is SO4, and our charge for sulfate is 2 minus. Sulfite is SO3, 2 minus. So I ate more just means there are more oxygen for every single 8 or sulfate. Same thing goes for phosphate and phosphite. I'll show that. So and actually I have it right here. Phosphate and phosphite, that 8, I want you to still think I ate more, just meaning there's more oxygen. And the 8s will always have one more oxygen than the ites. So when you're trying to remember all the different polyatomic atoms, that's actually a cool trick that I used, that I really only had to remember all of the 8s, and then all the sulfites or ites then were always one oxygen less, and it works for everything. So same with nitrate, that's always one oxygen more than the ite. Cool. All right, so continuing on with this type of polyatomic atom and ionic compound. So if we were to have calcium and phosphate, calcium has a 2+ charge, while phosphate has a 3- charge. We're going to do that same lasso or kind of just balancing of our charges. And the only difference here is that every single polyatomic will be in parentheses, and we will place our subscript on the bottom or outside of the parentheses. And then we'll see it's calcium 3 and then phosphate in parentheses with that too. Okay. So continuing on, there's still more. The other one would have been ionic compounds pretty much with everything. So we have a transition metal, our name of our transition metal. All right, transition metal, our Roman numeral, and our polyatomic atom. So it really incorporates everything that we just talked about. So in our case, we'll have copper 2. That 2, or Roman numeral, refers to the charge of our transition metal. And then next, our polyatomic atom, in this case, would have been nitrate, so NO3-. And this one's a tiny bit different. We didn't have to balance out the charges for copper, since that's already 2+. I really just needed to put a 2 with nitrate. So we would have just had nitrate in parentheses and that 2 outside of the parentheses. So that was all the different types of combinations for ionic compounds. Like I mentioned before, ionic compounds, you always have to balance out the charges. For those of you who are just joining in, I went over ionic compounds. If you missed it, I also have actually just released a video on this. So that's already up on YouTube. All right. So let's move on to covalent compound. Actually, I believe there it is. I actually had an example before we move on to covalent compounds, and I actually have a poll up. So that poll that you see is just if you could answer this question. So go ahead and try out to go ahead and try this problem. Okay, and I just erased it. Okay, go ahead and try this problem. So write the name of this compound, and then when you're ready, just have that poll. I really released that poll, so just answer that question. All right, and then I also left, in case you don't know your polyatomics just yet, I left the chart on screen. All right, does anyone else need any more time? I think we might be good, so I'm going to go over this problem. All right, so going over this problem, it's going to be here, Ni2 SO4 3. Okay. So one thing to notice, this is ionic. We know that because this is actually a transition metal, and we'll see that these types here are all transition metals. So nickel falls under that category. We know that any sort of transition metal will have a Roman numeral. So Ni is actually nickel. Now, SO4 is a type of polyatomic atom. SO4 is sulfate. Not done yet. We will need a Roman numeral just because we do have a transition metal. So to figure out the charges of something that's pretty much really balanced for you, it's like you're going in reverse. So what we would do is we would actually have to know that sulfate's charge is a 2- charge. But my trick is just kind of go backwards, where that 2 charge was with our sulfate, and that 3 must have gone with our nickel. So this initially should have been nickel 3 plus and SO4 or sulfate 2 minus. So right then and there, we see that that would have been a 3 plus charge. So we need a Roman numeral of 3, and that's the correct answer. All right, now moving on to covalent compounds. With covalent compounds, they are different. Remember that those consist of 2 nonmetals, and you never balance out your charges. Okay, that's the biggest thing I would say for covalent compounds. You do not have to balance out charges, as well as you do need to know all of these prefixes 1 through 10. Those are the most common ones. If we were given an example here, I want you to notice that this is going to be our prefix always in front, then the name of our nonmetal. And then continuing on, there's going to be another prefix plus the name of our nonmetal, and it's going to end in "ide" again. So for example, if we had diphosphorus pentoxide, that di just refers to 2. That pent refers to 5, as we see in our prefixes, right here and here. And then all that's saying is that there are 2 phosphorus, and then there's 5 oxygen. So that's why it's P2O5. All right. Any questions on naming? Is this making some sense? Go ahead and write in the chat. Yes. Jessica says yes. This is making sense. Cool. Chris says yes. Okay, so I'm going to go ahead and move on to just different types of reactions. This is my little trick and tips to you guys. The first type of reaction is known as either combination or synthesis. So how I like to look at this is it's going to consist of only one element. So in our case, we really just have nitrogen. And then we also have, it's going to be added to one other element. So in our case, hydrogen. Then that's going to form one compound. That's how you know it's combination or synthesis, when we have one element plus another element equaling one compound. The other type is decomposition, which is actually the reverse or the opposite of combination, where we instead start off with one compound, and then we break those apart, or we decompose them into one element plus another element. That's decomposition. And these are just helpful hints to figure out how you know what type of reaction it is overall. The next one is called single replacement, also known as single displacement, where you start off with, you at least have one compound, and then you're adding one element. So this was one compound, this was one element, and it forms one compound, one element. And you'll notice with single replacement, what's actually occurring is it's like you're kind of swapping these two, meaning our aluminum and iron kind of swap with each other, and then this forms aluminum oxide, and then the iron's left alone. So that's why they call it replacement, because you're replacing aluminum with that iron. Then there's another one just like it, where it's called double replacement or double displacement, where instead we start off with two different compounds being added to each other, and they form two completely different compounds. So in our case, we would actually swap these. So we would swap our sodium with our chlorine, and then we'll swap our barium with our OH. Those two combine as well. I will be showing you guys soon how to predict your products, just meaning how, if you're just given reactants, how they can then form the products. And the last one I'm going to go over is combustion. This is a special case where we always start off with a certain type of, it's called a hydrocarbon. Hydrocarbon just meaning that hydro means it has a hydrogen, and carbon meaning it has a carbon. So in our case, this is a hydrocarbon. There's a certain amount of carbon, a certain amount of hydrogen. But it is always going to be added with an O2, and then it's going to produce CO2 and water. So that's going to be your biggest hint right here, is if you wanted to identify if it's combustion, just what I boxed in, looking at that, that'll tell you it's combustion. All right. So moving on to how you can predict the products. Let's say if we were just given these overall reactants, and we wanted to predict first off what type of reaction it is, as well as what's our product. So in our case, since we see that this is one compound plus one other compound, it then has to produce one compound plus another compound. So in our case, this is going to be double replacement or double displacement. Then I'll show you, if I don't erase it first, I'll show you how we're gonna do this. So let me not erase it. Come on. There we go. Okay. So I like to think of this as, it's like you're foiling in a way. I tend to relate some things to math just because you guys have gone through that before. So I want you to think of like the inner and the outer of foiling. So our inner with our inner, so these are going to combine to form a compound. And then our outer with our outer will also combine to form another compound. So to begin with, I'm going to always start off with putting, so as a note, always start off with putting your metal, which is positively charged, and your non-metal comes at the end, and that's negatively charged. So in our case, Na, or sodium, will be our metal. Sodium has a +1 charge, and chlorine will be our non-metal with a negative charge. Something I want to note is that this 2 does not come along with it. That 2 was only there to balance out barium chloride, and it's not going to go on with forming our next compound. So then what we notice is that we'll have NaCl as our new product. Then moving on to the outer with the outer, barium will be our metal, and then hydroxide, and also barium has a charge of 2+. Hydroxide, or OH, will have a charge of -1. We need to balance out these charges since they are ionic. This is ionic compound. And then I'm just going to move this 2 to balance out the charges. And this is going to be barium hydroxide. Remember, with polyatomic atoms, they will have a 2 on the bottom. So polyatomic atoms, they will have, they will be in parentheses after you put that 2 on the bottom. So barium hydroxide, that's going to be our new product. Okay. So now we have to balance it out. Now that we got this down, okay, I'm just going to balance everything out. And then what I like to do with balancing is I always leave the polyatomic atoms together. So in our case, our polyatomic atom will be that OH. And I'm going to leave that together, and I'll show you what I mean. So I write down on the reactant side just all the different atoms that we have, or all the different elements that we have. And I'm going to leave OH together. So any polyatomic, leave together just to make it easier. And I'm going to do that same thing on the product side. So in our case, barium there's only 1 on our reactant side, and chlorine has 2. I see that with that subscript. Next, Na has only 1, and OH is also 1. And then looking at our product side, barium there's only 1, chlorine 1, Na 1. However, this 2 on our hydroxide tells us that there are 2 OHs. So then balancing this out, I'm going to start with balancing out chloride. So then balancing out chlorine, I'll look at the product side, and I'm just going to place a 2 in front. And this is always going to multiply. It's going to multiply to our chlorine. So meaning there's now going to be 2 chlorine overall. And I'm just going to rewrite that. Next, this also affects the Na. So now there's going to be 2 Na as well. And I'm just going to rewrite everything else that I originally had. So we're not done yet. Next, we have to balance out our sodium as well as our hydroxide. And doing so, I'm just going to place a 2 in front of that sodium hydroxide and see if that balances everything out. So this will affect our Na, that'll be a 2, and OH, that will also be a 2. Because I want you to think of this as like you're distributing, and that affects both of these different elements. And then next, chloride also still has 2, barium only has 1, and yep, it checks out, we're balanced. Any questions so far? Let me know in the chat how you guys are doing, if you have any questions, or is this making sense? All right. Can we do one more? Sure, Jessica. Jessica, did you want to see more of balancing or predicting the products? Balancing. Okay. Sure. So let's do another. And better yet, let's do one that I have seen a lot, and this might even have a fraction. I say that just because I have seen those on exams. Here, let me write that out. All right, we'll balance out this one. Okay, so I'm going to balance out this combustion reaction. And once again, so one thing, there is no polyatomic atoms on either side. So I do have to break everything apart, meaning I'm just going to put the name of every single element for each side. On the reactant side, we only have 2. This 2 tells us that. And then on for hydrogen, we only have 6. For oxygen, we have 2. Next, for our product side, we're going to add, and actually before we do that, we only have 1 carbon. We have 2 hydrogen, and our oxygen, we'll add these 2 together. So we have 2 plus this 1, giving us 3. Okay. So I always recommend leaving oxygen for the very end. So, and as well as even hydrogen. So I'm going to start off with balancing out carbon first. And I'm just going to place a 2 in front of that CO2 to balance out our carbon. And then note that this is actually going to distribute and affect both of these. So I'm going to recount that there are now 2 carbon. And then I'm going to recount how many oxygen I have. There are 2 times that 2, so there's 4 here, plus the 1 that we initially had with water. So we actually have 5 oxygen. And then nothing changed for hydrogen. And then we're still not balanced. So then I'm going to look and see, okay, I'm going to try balancing hydrogen, because you always leave oxygen to the very, very end. And then I'll put a 3 in front of that H2O. The reason why I'm putting a 3 is because these 2 multiply, and so after we distribute both of these, that 3 to both of these elements, we now have 6 hydrogen. So we're getting closer. And then I'm going to recount oxygen all over again. And we still have 4 on this side, plus 3 on this other side with our water. That gives us 7. Nothing affected our carbon. So still not done. And you'll notice that this actually could keep on going pretty much. It's endless. It just keeps going on and on. And what we're actually going to do, since this is a 7 and there's 2 on our oxygen on the reactant side, is we have to use a fraction, unfortunately. And I'll show you how to do that. So since there's no way of balancing out this perfectly, I will place a fraction, and I'm just going to use this 7, and I'm going to say 7 halves. So 7 halves, we're then going to multiply everything by 2 to get rid of that denominator of 2. When I do that, this will then distribute into every single coefficient. And I'll rewrite that. So our new answer would have been 2C2H6 plus 2 times that 7 halves. The 2's cancel, giving us 7. And that's now O2. And then 2 distributing with this 2, that becomes a 4, CO2. And the 2 multiplying with the 3 becomes a 6, H2O. And we're balanced. All right, making some sense? Jessica, how was that? Yeah, that was probably a lot because it's a fraction. Okay, it's better. Cool. And then if we understood that, that's pretty much the hardest it's going to get with fractions for balancing reactions. Everything else is a bit easier. All right. So I'm now going to move on to the main event, which is stoichiometry. Okay, so stoichiometry, this is actually really similar to unit conversion or dimensional analysis. It's just now incorporating a lot more of the chemistry side to it. So we still will have conversion factors, and just recall that conversion factors are it's pretty much just something that allows us to go from one unit to the next, right? A conversion factor, if we remember, it has 2 different units. So I'm going to be going over all the different types of conversion factors we will see in stoichiometry. So our first one is known as molar mass. And molar mass just means it's really just the mass of an element or a compound, and its unit is going to be grams per mole. So right then and there, we see that since it's grams per mole, right, this grams per mole has 2 different units, so that's going to be used as a conversion factor. And then I will be let's go over molar mass real quick. So like, let's say if we wanted the molar mass of water, how you would do this is you would look at your periodic table and then you would write out how many of each element there are. So hydrogen's mass is 1.01 roughly. Now that there are two, we'll multiply 2 times the mass of one hydrogen. And then that'll give us 2.02. And then we'll add that to the mass of just one oxygen, so 16. So we'll add these two together. And then our molar mass would be that it's 18.02 grams per mole. That's just how you identify what the molar mass is. Okay. And then I'll go into, let me erase this. So I'm going to go into when you will use that, when you know when to use molar mass or not. The main thing to note is whenever we're going to use molar mass, your clue is whenever we're going from grams to moles or moles to grams. So I'm going to say that again. You know when to use molar mass whenever you're converting grams to moles or moles to grams. Okay. And we'll do some practice problems on this. The next conversion factor that we're going to see is something called a mole-to-mole ratio. So this is where your balancing skills come in. We always have to use a balanced equation for a mole-to-mole ratio. And all that's really saying is, let's say if we were to have some sort of, let me actually go back to these different types here. This will make some more sense. There we go. So let's look back at this type of reaction decomposition. So a mole-to-mole ratio is really saying this. For every 1 mole, because there's really an imaginary 1 here since there's no other coefficient, for every 1 mole of, let's say, C2H6, that is then equal to 2 moles of carbon. So it's really just looking at your balanced equation to determine how many moles of each, goes hand in hand. And that's kind of why we call it a ratio, because we have 1 CH6 and then per every 2 moles of carbon. We could also say the same thing for there's 1 mole of C2H6 for every 3 moles of H2. So I'm gonna show that really for a mole-to-mole ratio, you know when to use this whenever you're trying to change the compound or the element altogether. So whenever you're changing your compound, like in this case, we're going from C2H6 to carbon, then and this is moles, you know to use a mole-to-mole ratio. And how do we find that? From our balanced reaction, okay? All right, so going back to that, whenever you're changing compounds or whatnot, use our mole-to-mole ratio. And our last one is Avogadro's number. Avogadro's number has a bunch of different units. I know they have particles, atoms, molecules, formula units. That is always going to go with that 6.022 times 10 to the 23rd. So that could be, particles, atoms, molecules, formula units. Those are interchangeable. And it's then going to always equal 1 mole. All right. So I'm going to go over those clues again. You know to use molar mass, or really the mass of the entire compound, whenever you're going from grams to moles or moles to grams. You know to use a mole-to-mole ratio whenever you are changing your compound altogether. And where you find that is it's the coefficients or the numbers in front in your balanced chemical equation. And then Avogadro's number is always going to be when you're converting particles, atoms, molecules, formula units to moles or vice versa. Okay. All right. So let's try one. All right. So putting it all together, as always, as you guys probably know by now, I always write our given and then what we're finding. So our given in this case, how many grams of potassium chloride are in 9.2 particles? So our given is that 9.2 particles, specifically of KCl, or potassium chloride. And then we are then finding it says the grams of KCl. Okay, I'm going to start with just developing a plan. And we know that our first unit, the unit that's given, are the particles of KCl. And then we're trying to jump to grams. And then kind of like what we were doing before with like unit conversions or even the metric system, is there has to be some sort of in between or some sort of bridge to allow us to go from particles to grams. We can't just instantly go there. And what's always going to allow us to do that is moles. So we'll convert particles to moles of potassium chloride, and then finally get down to grams of potassium chloride. And then I'm going to go one step further and even tell you what the conversion factors you will be using in between. So as we mentioned, whenever we're going from particles to moles or moles to particles, you will be using Avogadro's number. So Avogadro's number goes here. And then, so that would have just been our first conversion factor. Next, as we go from moles to grams, remember, moles to grams or grams to moles, you use the molar mass. So our molar mass would be our conversion factor in this case. All right, so let's set that up. Any questions so far? How are we doing? This making sense? Yes, Jessica says yes. All right. So I'm just going to start with our given, that 9.2 particles of KCl. And then we always want to align our units across from each other. So particles will be on the bottom, particles of KCl. And then I would say get used to writing the compound's name, because there will be some, that's actually the next one, where we're changing the compounds altogether, and it starts to get confusing if you forget which compound you started with or ending with. So just make sure to write that and get used to doing so. Continuing on, so we'll have our particles across from each other. That's per every mole of KCl. We said our first conversion factor was using Avogadro's number. Remember, Avogadro's number is 6.022 times 10 to the 23rd per every 1 mole. And that'll be on top. And then we'll notice that our particles would then cancel. Not done yet. We need one more conversion factor. So we'll align our moles across from each other so they can cancel. And lastly, our grams on top. So that would be our final answer. And then we do need to figure out the molar mass of potassium chloride, and we'll do that now. So the molar mass of potassium chloride, potassium, looking at our periodic table, has a mass of 39.10. And then chloride has a mass of 35.45. We'll then add these two together. And then we get 74.5 grams of potassium chloride. You know what? I rounded. Let me actually add those up right now. So 39.1 plus 35.45. There we go. 74.55 grams per mole. So our grams will have the 74.55. All right. And then from there, we will multiply the 9.2 times that 74.55 and divide it all by 6.022 times 10 to the 23rd. So I'll do that now, just multiplying that out and dividing it by Avogadro's number. And we end up getting 1.138 times 10 to the negative 21st grams, but we still have to pay attention to our sig figs. So going back to our original question and our given, we have 2 sig figs, so we're going to end with 2 sig figs. So our final answer, going back to this, our final answer would then be 1.1 times 10 to the negative 21st grams of potassium chloride. All right. Okay. Any questions here? I was planning for us to do another one. I'm going to erase this and give myself a little bit more room. And then we'll continue on with another one where good so far. Thank you, Chris. All right, I will be doing another one. And then here, let me go back in. All right, so we're going to practice some more balancing as well as stoichiometry overall. And then this one, I believe, does consist of actually changing the compounds altogether. All right, so let's see what we got. What mass of carbon dioxide is produced when 6.2 moles of propane, or C3H8, is burned in oxygen? Okay, so even before starting, they at least were nice enough to give us our equation. However, it's not balanced. So let's start off with just balancing out this reaction. So this is a combustion reaction, right? You can also notice that it says burned. Whenever something's burning or on fire, it's going to be combustion. And then we could have also seen that O2 and CO2 plus water. So like I did before, balancing reactions, just going to write out on both sides how many of each element we have. And then on our reactant side, there's going to be a total of 3 carbon because of that subscript. There are 8 hydrogen, once again, because of that subscript, and then 2 oxygen. Next, we only have 1 carbon on our product side, 2 hydrogen, but 2 plus that 1, 3 oxygen. All right, so I always leave oxygen and hydrogen to the very, very end. So I'll start off with just balancing out carbon. Placing a 3 in front of that CO2, that'll change carbon to a 3. And then remember, we're actually going to distribute or multiply that 3 with that subscript of 2. This would give us 6 on this side, but there's still that 1 on the water. And then we're going to have 7 oxygen overall. And that 2 remains again. Okay, so still not done. Next, I'm going to go in order and actually balance out hydrogen. So we want to get 8. I'm going to put a 4 because that has to distribute or multiply. So 4 times that 2 now gives us 8 hydrogen. And sadly, I have to recount all the oxygen. Okay, so we still have 6 for our CO2, but now we're going to have 4 times really that 1. So there are 4 on this side. So we have a total of 10 oxygen. And then our carbon stayed the exact same. So then finally almost done. We need 10 oxygen on our reactant side. So we need something to multiply with that 2. 5 times 2 gives us 10. So just rechecking everything. Yep, we are balanced. All right. Now that we finally are balanced, we can actually do the question now. And we'll write down what we're given, what we're finding, and all of that once more. So our given and what we're finding, and then we'll develop a plan and go from there. So once again, I'm going to reread the question. What mass of carbon dioxide? So right then and there, it told us what we're looking for. We're looking for the mass of carbon dioxide. That also really refers to the grams of CO2. So our naming skills are always going to be coming into play. So carbon dioxide, real quick. Remember that this is actually a covalent compound. Carbon being one of our nonmetals. And then since there is no subscript, it's really just going to be carbon. And then now di, meaning 2. Oxide, that "ide" refers to 1 element. And then we'll just have oxygen, and there's 2. So that's how I knew it was CO2. All right. So we're looking for the grams of carbon dioxide. And then we are given, so is produced when 6.2 moles of propane. So we have 6.2 moles of propane, which is that C3H8. All right. So we're going from moles of one compound to grams of a completely different compound. So somehow, some way, we know that we're going to use a mole to mole ratio because we are changing our compounds. So I'm going to start off with our plan. And our plan will begin with just the moles of propane, or C3H8. And we're going to see what we're going to do. So I mentioned that if we're trying to change the compound, we need to do a mole to mole ratio. So we already have this in moles. I'm going to do a mole to mole ratio to be able to get the moles of CO2. So I just changed my compound. Next, we want to figure out what our grams of CO2 is. So then I'm going to go to grams of CO2 since we figured out that, or actually we got down to the compound that we want to find. And I'll show you what we do all in between. So this first part, we said whenever we're changing the compound is a mole to mole ratio. So mole to mole ratio, and we use our balance equation. That's why we started off balancing all together. Next, if we're going from moles to grams, remember that's using molar mass, specifically of CO2. All right, so we'll set this up. Always starting with your given, that's 6.2 moles of C3H8. All right. And then we're going to use our mole to mole ratio. So I'm going to go back to our balanced equation. And then if there's nothing in front, that just means there's a 1. All right. So in our case, there is 1 mole of C3H8 for every 3 moles of CO2. So that will be our mole to mole ratio. And I'm just pulling those numbers from our balance equation. All right, so going back, we'll place the moles of propane, C3H8, on the bottom. And then on top, we'll get 2 moles of carbon dioxide. So we said there's 1 mole of propane for every 3 moles of carbon dioxide. And then lastly, so this is our first conversion factor. The next conversion factor we said was molar mass. We'll put the moles of CO2 on the bottom again to cancel. And lastly, put our grams of CO2 on the top. So we need to figure out what our molar mass of carbon dioxide is. So I'll do that here. Carbon has a mass of 12.01. And then oxygen, we have 2. So we'll do 2 times the 16, the mass of 1 oxygen. This then gives us 32. We'll add these 2 together, and then we'll get 44.01 grams per mole, and that's the molar mass of CO2. And I'm just going to put that on top. So this would have been 44.01 per every 1 mole. Okay. Last step is to multiply. So multiply straight across. Let's see what we get. And then remember, we will be rounding to the appropriate amount of significant figures. So let's see what we get. Your answer would be 818.586 grams of CO2. However, our given was only 2 significant figures. So we're going to change this to scientific notation. So whenever you have a larger number, and yet you started off with a small amount of significant figures, and you're trying to figure out, well, I can't just change this to 82 grams because that doesn't mean the same thing as 818. You would then just change this overall to scientific notation. Scientific notation. So in our case, I'll show you how to do that. Just going to move over that decimal. Moving this over 1, 2, stopping here. And this gives us 8.18586 grams of CO2. I'm going to round to only 2 sig figs. So I will round up. This would have given us, I totally forgot the 10 times scientific notation. There we go. So I move this over 1, 2. This would have been 10 to the second grams of CO2. Round this up, 8.2 times 10 to the second grams of CO2. And we found our answer. questions here? I realize I have a little bit of time remaining. Let me know if you guys have any more questions. I'm going to start answering some of your questions now. Let's see. All right, so let's see. Luce, I'm going to start answering your question right now. Do you have any tips on remembering element charges when they're not labeled on a periodic table? Okay. So that does go back to, let's see if it's not labeled here. Let me go back to our charges overall. And not erasing that. Okay. So I know that they're really not going to give you, like on your exam, right? They're not going to give you the charges. So how I remembered it was really just seeing that these two here are always going to be positive because those are your metals. And just knowing that we're going to start with +1, +2. And then we're also going to have +3, and then it goes down. So it's really the opposite, just knowing it's 1, 2, 3, and it's positive. Then it goes -3, -2, -1. So that I will say is something you sadly do have to memorize. If you were talking about your polyatomic, a trick for that is I mentioned it in the beginning, where let's say if you're trying to figure out, how many oxygen are within, or even the charges, actually the charges. How I remember this is I really just write it all down. So flashcards personally never worked for me. How I like to do this, and it's exactly how I wrote them now, is I align them according to charges, and I just rewrite them over and over again. Like ammonium is the only one with a +1 charge. And then everything thereafter, has a charge of -1. And then really just remembering, you could also even just remember the most common ones, like let's say carbonate and chromate, sulfate, sulfite, those have 2-, and your phosphate or phosphite has a 3- charge. So just seeing like the differences, the majority have a -1 charge. So that's one way of remembering them. Another thing is with naming, whenever we have something that's a transition metal, that will give you a Roman numeral that does tell you the charge. The other thing I can tell you to really answer your question is, let's say if we were to have ferric versus ferrous. I've seen that too with naming, where the ick always has a higher charge than the us. So that's another way of looking at it, where ick, this actually would have been a +3, and us is always one less than the ick. So that would have been +2. So it kind of chops everything in half as to what you have to remember. If you just remember the ick is always one more than the us, or vice versa. All right. And then I also believe that answers Chris's question as well. And Chris also, just looking at what I mentioned before in the beginning, that ide versus the ate and the ite, right? Where I talked about sulfide, sulfate, and sulfite, that ide referring to only one element, like let's say just sulfur, and then that ate referring to there's going to be more than one element, that's a polyatomic atom, where it would have been SO4 2-, and then our ite would have been always one less oxygen, so that would have been SO3 2-. And my trick was that I ate more. So the ate will always have one oxygen more than the ite. So that kind of actually chops everything that you have to memorize in half. So if you just remember all of the eights, like sulfate, phosphate, nitrate, if you just remember those, and just know that the ites or the sulfite or nitrites will always be one oxygen less. That's a tip for you. All right, let's see. Do you have any? You're welcome, Chris. Do you have any tips on how to for chemistry exams? All right, let's start answering that, Jennifer. So I know sometimes they give you study guides, and other times, well, At least when I was in college, I never got study guides in general. That kind of tells you the professors I had. So what I would typically do is just look at all the topics that we covered and then make sure to redo all the different practice problems that I can find for that specific topic. And then what I actually even did, because I personally even had testing anxiety whenever I'd take exams, and I found a way to conquer that, was I would actually time myself, and I created my own exams. So I found like different problems, and I tried to kind of like answer them and I time myself. So I put myself in that setting. So I never, would actually run out of time, because before I used to run out of time for my exams. So that's something that I personally did, and it worked for me. But as I mentioned, just a lot of practice problems. And that's actually why I place practice problems in every single one of my videos. Those are common questions that I actually have seen on so many exams overall, whether it be in high school or college. So I hope that answers your question, Jennifer. All right. And Jessica, I see your question, and I will start balancing out this for you. All right. Let's see. We have copper. Okay. How would I balance out this one with parentheses? Okay. So let's see. We have copper sulfate and we have zinc nitrate. All right. So once again, this is predicting products. And this is the concept of foiling, where my trick was it's going to be the inner with the inner, because this is double replacement. And then the outer with the outer. And those two will combine to form a compound. So in this case, our zinc is our metal, because we always put the metal first and then the non-metal. Now, zinc, we had to see what is the charge of zinc, since that is a transition metal. And how I'm going to figure that out is I'm going to go back to this actual compound, and I'll see that this too would have gone back. Okay. And looking at that, that just meant that, let me rewrite that. That just meant that this had to have been zinc 2+, and then nitrate is a -1. So that's where I get my charge. So zinc is that 2+. And then next, sulfate, SO4, is a 2- charge. And that was something, sadly, we just have to know. All right, so that would be that first compound that we'd make. So zinc sulfate. And then next, I'm going to continue with our next compound. So we'll have copper, and then we'll have NO3. And once again, I'm going to predict the charges that we would have had and would have seen. So sulfate has a charge of 2- typically. So since there is no subscript here, that just tells me that it would have been neutral, or copper should have been a 2+ charge to cancel out that -2 charge. So here I see this would have been a 2+, and then nitrate would have had a -1. We're not balanced, right? So I need to kind of lasso that 2, and this would have been Cu parentheses NO3 2 on the outside of our parentheses. That is our new product, a new compound that I will add there. And then I'm going to balance this out. And that concept, once again, with our polyatomics, where whenever we're balancing, we do not want to break them apart. And I'll show you guys what I mean again. Let me zoom in. All right. So we'll balance this out. So once again, I'm not going to break apart any of the polyatomic atoms. In our case, this would have been so far copper. And then I'm going to leave that SO4 intact. Zinc and NO3, that's our other polyatomic. So whenever we have two polyatomics on the opposite sides and they aren't broken apart, don't break them apart when you're balancing. Same thing goes for that nitrate. Okay, I'm going to rewrite that on the other side, and then we'll get to balancing. Okay, so copper has, there's only one. Sulfate, there's only one because there is no parentheses. That 4 just was part of our sulfate. And then zinc, there's only one. However, nitrate, there is 2 because it's outside of the parentheses. All right, next we have 1 copper on the product side. We have 1 SO4, and then we have 1 zinc, and lastly we have 2 nitrates. So in our case, it looks like we're balanced. Yep, that was actually nice. You're balanced, actually. So I think it could have just been predicting your products. That was the tougher part. All right, does that help, Jessica? Hope that helped. Yes, you're welcome, Jessica. All right, guys. So it is 8 o'clock, at least for myself. It's been an hour, and hope that helped for everybody. I will be doing this again next Sunday, going over other topics. Go ahead and save your spot for next week. I will be going over empirical and molecular formulas, as well as limiting reactants, excess reactants, and percent yield. All right, so click that button, save my spot for next week, and I will see you guys next time. And I also will be putting more and more videos coming up this week. So thank you for joining, and I'll see you guys next time.